Okay, so first of all, the free body diagram in part A is simply the mass m with the force of the earth on m downward and the normal force of the hand on the mass upward. And if you didn't put this in, I didn't take off, but technically speaking, that is abiding by the this is in agreement with the words that I use. Note that the object and agent are indicated for each force. So part B asks for what the weight of the mass is, and the weight of the mass in this situation is simply the force of the Earth on the mass. And so to do that, you need to use Newton's law of gravitation, which is g times little m, the mass of the little mass, times the mass of the Earth, divided by the radius of the Earth plus the distance away from the surface of the Earth. This number right here is the distance the mass is away from the center of the Earth. And so if you plug numbers in here, 6.67 times 10 to the minus 11 times 2 times 10 to the 2 for little m, 5.97 times 10 to the 24 kilograms from the constant that I gave you up here. And then in the bottom goes the radius of the Earth, 6.38 times 10 to the 6th meters. And you need to convert this 1,000 kilometers to meters, and that's 1 times 10 to the 6th meters. So please take careful note that 1,000 kilometers is 1 times 10 to the 6th meters. And so the result of this calculation is 1.46 times 10 to the 3rd newtons is the force of the Earth on the mass. The instantaneous acceleration is then in part C is then simply an outcome of Newton's second law. Acceleration is equal to force divided by mass. So I can take this net force, this weight that I just calculated, and when I release it, then the free body diagram is simply just going to be the force of the Earth on the mass. That will be the net force. And so the net force, when I release it, is this instantaneously divided by 200. So it's 7.31 meters per second radially inward. Note that this is a little bit less than 9.8 because the force is less than it ordinarily would be at the surface of the Earth. Okay, D was a hard one. Basically, you had to give a lower and upper estimate for what the velocity of the mass would be when it hit the Earth. And so the basic idea is to use your kinematic equations. V squared is equal to v squared naught plus 2 times a sub y times delta y. And so the upper limit, the lower limit for the velocity would be the lower acceleration at the higher altitude of 1,000 kilometers that we calculated. And so that would give you a velocity when it hit the Earth of 3.82 times 10 to the 3rd meters per second, and then the upper would be assuming 9.8 meters per second, and again 1,000 meters for the delta y. In which case you'd have 4.43. So you have 3.82 and you have 4.43, and so a pretty good estimate of what the velocity when it hits the Earth would be simply the average of these two, which turns out 4.13. Okay, so let me scroll down a little bit here if I can. So this one, now you have the same 200 kilogram mass, but it's in a circular orbit 1,000 kilometers above the Earth. And draw a free body diagram for the mass. The only force acting on that mass is the force of the Earth on the mass. It's radially inward, and that, of course, is what provides the centripetal acceleration that's pointing inward from Newton number 2. The weight of the mass is just what was calculated before. 1.46, calculated exactly the same way. The instantaneous acceleration is, again, it's the same one that was calculated above. Same reasoning, Newton number 2. In this case, it's the centripetal acceleration, however, but its value is the same. What's the velocity, magnitude, and direction? Well, we know that v squared over the radius is going to be equal to big G times the mass of the Earth divided by the radius from the center of the Earth squared. And so in each case, this is the Earth radius plus the height above the surface of the Earth, and ditto for this. And we can solve this for V, in which case we get this equation: square root of G times the mass of the Earth over the distance of the mass from the center of the Earth, which is R sub E, the radius of the Earth, plus the height above the surface of the Earth, and that is 6.67 times 10 to the minus 11 times the mass of the Earth, 5.97 times 10 to the 24th kgs, and then in the bottom is 6.38 times 10 to the 6 plus 1 times 10 to the 6. And that turns out to be 7.35 times 10 to the third meters per second, and it's tangent to the orbit. Once you have the velocity, the period is just the circumference divided by the velocity. The circumference is 2 pi times the radius of the circle from the center. Again, that's R sub E plus h divided by this velocity that was just calculated. So if you work the numbers here, 2 pi times the 7.38 times 10 to the 6 meters, which is this right here, divided by 7.35 times 10 to the third meters per second. And that ends up being 6.31 times 10 to the third seconds. Converting that to hours with this conversion factor is 1 3/4 hours. Okay, so this next one was about a planet called the Heart, which has a mass of twice the Earth and a radius of twice the radius of the Earth. And so you're doubling the mass and doubling the radius. And what's the acceleration of the gravity? Well, okay, so the acceleration of gravity on the planet Heart is big G times 2 times the mass of the Earth divided by 2 times the radius of the Earth, the quantity squared. And if you work that out, that's 1/2 of this quantity. But this quantity is just the gravitation of the acceleration of the Earth. And so since that's 9.8, this is 4.9. And this also shows that you don't really need to know R sub E and M sub E to get this part of the answer, because you can recognize this as being the gravitational acceleration of the Earth, and therefore it's just 1/2 GE. Okay, so let's go to the back page here. So on the back page, you had a ranking task here, and the way these rank are, again, this is a straightforward application of the Newtonian law, gravitational law, is F sub A is this, F sub B is this, which is 2 times F sub A, because you've got this factor of 2 here. F sub C is also 2 times F sub A, so far these two guys are the biggest. F sub D, you're doubling M, but you're also doubling the separation between, and that turns out, since you have a factor of 4 on the top and 2 on the bottom, since you're squaring this whole thing, of 1/2 F sub A. So this turns out to be the smallest. These two turn out to be the two biggest, and this one's in the middle, which is what I say right here. Make sure you look through and understand the algebra there. It's basically just an algebra test. Okay, so the last one. Basically, we know that the larger the radius, the smaller the speed from this equation. And so that means that as you go to larger orbits, larger radius orbits, both the circumference is getting bigger and the speed is getting smaller, in which case this is going to have the largest period, and this is going to have the smallest one, and this one's going to be in between.